have been discussing about unit conversions from one unit system to different unit system, other unit systems, and we recall some of the unit conversions, like from how to convert from BTU to calories. 1 BTU is equal to 252 calories or 0.252 kilocalories, and 1 foot is equal to 30.48 centimeters, or in terms of meters 0.3048 meters, and 1 hour is 3600 seconds. 1 pound LB, 1 pound force is equal to 4.48 newtons, and 1 pound is equal to how many meters? 0.4536 meters, and 1 bar is equal to 10 power 5 pascal, or 1 bar is 10 square, that is 100 kilopascal, and 1 degree Celsius, 1 delta degree Celsius is equal to 1.8 delta degree Fahrenheit. Similarly, 1 delta Kelvin is equal to 1.8 delta degree Rankine. Okay, so with this, some of the numericals we can do are, so convert minus 40 degree Celsius to degree Fahrenheit, 25 feet square to feet square per hour to centimeter square per second, 100 BTU per feet square degree Fahrenheit or to calories per second meter centimeter square degree Celsius, 100 degree Celsius to Kelvin, degree Fahrenheit and Rankine. These 4 short numericals we will do now. Okay, let us take this first one, which is given minus 40 degree Celsius to degree Fahrenheit. Okay, what is that? Degree Fahrenheit is equal to 1.8 degree Celsius plus 32. Okay, so it is 1.8 into 40 minus 40 plus 32, which is equal to minus 40 degree Fahrenheit. This is A part. Let us take the B part. Convert 25 feet square per hour to centimeter square per second. To convert that, what is the conversion factor? 1 feet is 30.48 centimeter square into 1 hour is 3600 seconds. Repeating, 25 feet square hour, 1 feet is equal to 30.48 centimeters whole square into 1 hour is 3600 seconds, which is equal to 6.45 centimeter square per second. then Kelvin square Celsius. So report the values here. Okay, and then we have to do 100 degree Celsius to Kelvin, degree Fahrenheit and degree Rankine. What is that? 100 degree Celsius. So to convert 100 degree Celsius plus 273 Kelvin, and 1 delta degree Celsius is 1 delta Kelvin, is equal to 373 Kelvin. Okay. So that is conversion into Kelvin. To report it into Fahrenheit, what to do? 100 degree Celsius into 1.8 degree Fahrenheit by 1 delta degree Celsius plus 32 is equal to 212 degree Fahrenheit. Okay. To convert it into degree Rankines, what to do? 212 plus 460 into 1 degree Fahrenheit equal to 1 degree Rankine, equal to 672 degree Rankine. The same you can do directly also from 373 Kelvin. So what is the conversion? 1 delta Kelvin is equal to 1.8 delta degree Rankine is equal to 672 degree Rankine. Okay, I'm just repeating. So it is given 100 degree Celsius. To convert from 100 degree Celsius to Kelvin, we are adding 273 to it. That is, it becomes 373 Kelvin. Remember, they are in the same scale. 1 delta degree Celsius, 1 delta Kelvin is a thing. Okay. Similarly, to convert to degree Fahrenheit, 100 degree Celsius into 1 delta C is equal to 1.8 degree Fahrenheit plus 32 gives us 212 degree Fahrenheit. Similarly, 212 is Fahrenheit. To convert from Fahrenheit to Rankine, 212 plus 460 into 1 degree Fahrenheit equal to 1 degree Rankine equal to 672 degree Rankine. So 373 Kelvin multiplied by 1 Kelvin equal to 1.8 Rankine, which is 672 degree Rankine. So our next question is, convert 380 mm mercury vacuum into absolute pressure in tar, kilopascal, bar and pounds per square inch. How to do it? First we should know the relationship. Atmospheric pressure minus vacuum pressure is equal to absolute pressure. Okay. I'm repeating, atmospheric pressure minus vacuum pressure is absolute pressure. So to get absolute pressure, what is the in mm mercury? It is given in mm mercury vacuum. So what is the atmospheric pressure in terms of mm mercury? It is 760 mm mercury minus 380 mm mercury, which is equal to 760 minus 380 mm mercury. The answer is 380 tar. So yes, 1 mm mercury is 1 tar. Okay. So to convert this 380 tar, so other next we have done it for tar. Now we will do it for kilopascal. How to convert kilopascal? So now the absolute pressure is in 380 mm mercury, right? 380 mm mercury. So this is the absolute pressure. To convert to other unit system, 380 mm mercury we have to absolute, right? So it is absolute. Conversion factor is 760 mm. Mercury is 101.325 kilopascal, which is 50.654 kilopascal. Similarly, we can convert this 50.654 kilopascal as 100 kilopascal as 1 bar, which is equal to 0.5056 bar. Okay. Now we can convert this 0.5065 bar to 1 bar is 14.5 psi, is equal to 7.346 psi. So what is the answer? So we can express 380 mm mercury vacuum pressure as absolute pressure values of tar, kilopascal, bar and psi. The answers are, it is 380 tar, 50.654 kilopascal, 0.5056 bar and 7.346 psi. If you are looking at temperature scale, baseline is, if it is absolute 0, so we have minus 460 degree Fahrenheit, 0 degree Rankine. We have minus 460 degree Fahrenheit, 0 Rankine. We have 0 Kelvin and minus 273 degree Celsius. This is at absolute 0. Okay, so if you compare their value at, let me say, minus 40 degree Fahrenheit, so this will be 420 degree Rankine. We have degree Fahrenheit equal to degree Celsius at one condition, that is minus 40 degree Fahrenheit is equal to minus 40 degree Celsius. This is one comparison line at which that Kelvin will be 233. Okay, so then we have another scale where we have 0 Fahrenheit equal to 460 Rankine, 0 degree Fahrenheit, 460 degree Rankine, equivalent to 255 Kelvin and minus 18 degree Celsius. As I said, here this left hand side is degree Fahrenheit, right hand side is degree Rankine, here left hand side is Kelvin and right hand side is degree Celsius. Okay, so above which, if you consider the freezing point of water, what is that? 0 degree Celsius or 273 Kelvin. Okay, and the corresponding values are 32 degree Fahrenheit, 492 degree Rankine, which is freezing point of water. So next we can consider boiling point of water. Okay, boiling point of water is 100 degree Celsius, 373 Kelvin. Here it is 672 Rankine, 212 degree Fahrenheit. Okay, so that's what we did a numerical on. Convert 100 degree Celsius into Kelvin, we got 373 degree Fahrenheit, we got 212 and 672 degree Rankine. Okay, so this is the table. So what we observe here is delta. If it is delta, when you have delta Kelvin, what is the difference here? 100, 373, 180. 212 minus 32 is 180. So up to here. Here also. If you consider the delta T, what is the delta temperature in Kelvin scale? 373 minus 273 is 100. Delta K is 100. Okay, similarly in the unit of degree Celsius, 100 minus 0 is 100. So we have 100 delta K equal to 100, delta C equal to 100 in this region. Okay, only this region we have delta C equal to 100, delta K equal to 100 Kelvin. Okay, so coming to here, similarly if we consider in this left hand side Fahrenheit and Rankine, so the difference between the boiling point and the freezing point is 180. You can see here 180 Fahrenheit scale, 212 minus 32 is 180. So that way, so what we have is delta degree Celsius is equal to 100 delta degree Celsius is equal to 180 delta degree Fahrenheit. So that is delta C by delta F is equal to 180 by 100, which is 1.8. Similarly, delta K by delta R is equal to 180 by 100. So we get 180 by 100, which is equal to 1.8. So delta K by delta R equal to 1.8. So far we have seen the temperature conversion when it is delta T. Okay, but when it is actual temperature, how to convert from one unit system to another unit system, the conversion factors are given here. With reference to the same temperature table, the relationship between temperature Rankine and temperature Fahrenheit is given as temperature Rankine is equal to T Fahrenheit into 1 delta R by 1 delta F plus 460 degree Rankine. Similarly, to convert from degree Celsius to Kelvin, T Kelvin is equal to T degree Celsius 1 delta K by 1 delta C plus 273 Kelvin. And the relationship between T degree Fahrenheit and degree Celsius is T degree Fahrenheit is equal to T degree Celsius into 1.8 delta F by 1 delta C plus 32 degree Fahrenheit. Similarly, to convert from degree Fahrenheit to degree Celsius, it is T degree Celsius is equal to T degree Fahrenheit minus 32 into 1 delta C by 1.8 delta F. So these conversion factors we have to use when we have in any expression when we have temperature T. For example, specific unit terms, specific heat capacity Cp equal to some A plus Bt plus Ct square. Such expression, in place of T we have to replace from one temperature to another temperature term. Okay, so that in these places we have to make use of these conversions. Wherever there are delta T terms are there, from conversion from Kelvin to degree Celsius to Rankine to Fahrenheit, we have to make use of the conversion factor which we have seen earlier. So this conversion factor particularly is mainly for when we are expressing temperature of the system. Let us convert 100 degree Celsius to Kelvin, degree Fahrenheit and degree Rankine using the above four equations. Okay, we have to convert 100 degree Celsius to Kelvin, degree Fahrenheit and degree Rankine. So what is the formula? T Kelvin is equal to T degree Celsius into 1 delta K by 1 delta C plus 273 Kelvin. So which is equal to 100 into 1 by 1 delta K by delta C plus 273 Kelvin, which is equal to 373 Kelvin. Okay, so this is temperature in Kelvin. Now to convert to degree Fahrenheit, what is the formula? T degree Fahrenheit is equal to T degree Celsius into 1.8 degree Fahrenheit by 1 delta degree Celsius plus 32 degree Fahrenheit. Okay, so that formula we have written here is equal to 100 into 1.8 by 1 plus 32, which is equal to so and so Fahrenheit. That is 212 Fahrenheit. What is to convert from degree Rankine, 212 degree Fahrenheit to Rankine, we have to add 460 into 460 degree Fahrenheit into 1 delta R by 1 delta degree Fahrenheit, so which is, that is 212 degree Fahrenheit plus 460 degree Fahrenheit we have to add into conversion 1 degree for delta F equal to 1 delta R, so which is equal to 672 degree Rankine. Okay, so alternatively we know the Kelvin. How much Kelvin it is? 373 Kelvin. So T73 Kelvin is 1 delta K is equal to 1.8 delta R. So 373 into 1.8 gives us 672 degree Rankine answer. What is the answer in different units? So we have 100 degree Celsius is equal to 373 Kelvin equal to 672 degree Rankine equal to 212 degree Fahrenheit. Okay, that is the required answer. Before solving the next problem, let us recall the unit conversion for 1 British thermal unit. How much joules it is? 1 British thermal unit is 1055 joules. How much pounds is, how we convert pound to meters? We know that 1 pound is equal to 0.4536 kilograms or 453.5 grams. So for converting from Rankine to degree Celsius, we know 1 degree Celsius is 1.8 degree Rankines. Okay. So it is given that the heat capacity of sulfuric acid as a unit of joules per gram mole degree Celsius, and is given by the relation Cp is equal to 139.1 plus 1.56 into 10 power minus 1 T, where T is in degree Celsius. So we have to convert this unit from joules per gram mole degree Celsius to BTU per gram mole, pound mole degree Rankine, where in the right hand side the T should be in Rankine. Okay, let us solve it. Heat capacity of sulfuric acid Cp given in joules per gram mole degree Celsius, which is given as Cp equal to 139.1 plus 1.56 into 10 power minus 1 temperature in degree Celsius into BTU per pound mole degree Rankine, and temperature is in degree Rankine. So we have to convert this expression Cp equal to 139.1 plus 1.56 into 10 power minus 1 T, where Cp is to be in British thermal units per pound mole degree Rankine and T should be in degree Rankines. The first thing to do is left hand side Cp is given in joules per gram mole degree Celsius. This has to be converted to this. 1 British thermal units is equal to 1055 joules. Remember, what we are trying to do is we are trying to cancel this joule. So we have to write BTU in the numerator, 1055 in the numerator. For example, if you have to convert some 100 joule to BTU, in that case BTU will, some BTU is given, we have to convert to joule, then 1 BTU equal to 1055 we will write in the numerator. But here we are doing the reverse. Joule has to be converted to BTU. Therefore, we are writing BTU in the numerator. 1 BTU by 1055 joule. So this gram mole has to be converted. Okay. So gram mole in the numerator we have to do. What is that? 453.6 gram mole is equal to 1 pound mole multiplied by, here degree Celsius is there. So we have to do 1 delta degree Celsius is equal to 1.8 delta degree Rankine. So this degree Celsius gets cancelled, this gram mole and this gram mole gets cancelled. So what we have is Cp in 0.2388 British thermal units per pound mole degree Rankine. Okay, so this is the Cp value in SI unit is equal to given Cp value. When we multiply by 0.2388 we get Cp in terms of BTU pound mole degree Rankine. Okay, so how can I write it? Cp in degree Rankine is equal to Cp in degree Celsius multiplied by 0.2388. Similarly, whatever is given in the right hand side, so once we multiply by 0.2388 we get right hand side. Right now right hand side is whatever is given, we have to convert that internally, then finally we have to multiply it by 0.2388. Okay, so to do the right hand side, what is given is 139.1 plus it is given 1.56 into 10 power minus 1. For simplicity I am writing 0.156 T. This is in degree Celsius. Okay, so what is the conversion factor? We know temperature in degree Celsius is equal to temperature in degree Fahrenheit minus 32 into 1 delta C by 1 delta F. Okay, also we know that temperature in degree Fahrenheit is equal plus 460 is equal to temperature in degree Rankine. Therefore temperature in Fahrenheit is equal to temperature in degree Rankine minus 460. We are taking this to right hand side. Okay, also we know that delta degree Fahrenheit is equal to delta degree Rankine, delta degree Celsius to delta degree Kelvin, because they are in the same scale. Okay, so using this, what we can do, we can write temperature degree Celsius is equal to temperature degree Fahrenheit minus 32 into 1 delta C by 1.8 delta R. Further we can write temperature degree Rankine minus 460. Instead of TF we can write TR minus 460 minus 32 into this 1 delta C by 1.8 delta R. Actually it is delta C by delta F. We have seen that delta F is equivalent to delta R. Okay, so that way we can simplify this to write temperature in degree Rankine minus 492 divided by 1.8. When we further simplify 0.55 temperature in degree Rankine minus 273 is temperature in degree Celsius. Okay, so this is what we get the first equation. So now what we have to do is, so once we establish the relationship between temperature degree Celsius and temperature degree Rankine, in the given expression Cp equal to 139.1 plus 0.156 into Tc, we have to substitute. Okay, so we have to substitute this right hand side expression as 139.1 plus 0.156 within bracket 0.55 temperature in Rankine minus 273. Okay, so when you simplify 139.1 plus 0.0858 temperature Rankine minus 42.6 0.63. So upon simplification, what we get is 96.47 plus 0.0858 temperature in Rankine. So this is the right hand side we get. Okay. To get Cp in degree Rankine, we have to multiply this right hand side value by 0.2388 as we have seen already. So that is 96.47 plus 0.0858 temperature Rankine multiplied by 0.2388. We get the final answer 23.04 plus 0.0205 temperature, which is in Rankine. So we get Cp value in degree Rankine as this is the final answer. So let us do this one simple conversion. A rate of heat loss per unit area is given by rate of heat loss per unit area is given by Q by A, that is in BTU per hour heat square is equal to 0.5 delta T by power 1.25 divided by D in heat or 0.25. Convert this relation into kilocalories per second meter square, where delta T is in degree Celsius and D is in meters. So this is the question. So this delta T is given in Fahrenheit, which we have to convert to degree Celsius. This D is given in feet, we have to convert to meters. So that conversion we have to do in the right hand side. On the left hand side it is given BTU per hour feet square, so which we need to convert. So if we consider the left hand side, so what we have is BTU per hour feet square. So what are the conversion factors? 1 BTU is equal to, in terms of calories or in terms of kilocalories. Calorie means 252 calories. If it is kilocalories, 0.252 kilocalories into, what is the conversion factor for feet? You know that 1 feet is equal to 0.3048 meters. So this needs to be squared, multiplied by, this hour needs to be converted to seconds. 1 hour is equal to 3600 seconds. So this hour gets cancelled. So we have feet square getting cancelled. So what we get is this BTU getting cancelled. Okay. What we get is kilocalorie per second meter square. So whatever value we are getting is 7.5 into 10 power minus 4. So to get this Q by A in the new unit system, that is in kilocalorie per second minute system, what we have to do is we have to convert this QA given in BTU units into 7.5 into 10 power minus 4. Okay, so that means we have to do the same in the right hand side also. So after we convert the RH right hand side, we have to multiply it by 7.5 into 10 power minus 4. Okay, so let us first convert this given RHS, this 0.5 into delta T by D, whatever raised to the corresponding power, to delta T in degree Celsius, D in meters. Then after that whatever we convert, we have to multiply by 7.5 into 10 power minus 4. Okay. So in the right hand side, what we have to do is, it is given that 0.5 delta T power 1.25, which is in degree Fahrenheit, divided by distance given in feet 0.25. Okay. So that way we have to convert it. Is equal to 0.5 into, open it, delta T in degree Fahrenheit. Conversion factor is 1 degree delta C is equal to 1.8 delta degree Fahrenheit, right? So this is raised to the power of 1.25. Similarly, in the denominator, D is given in feet. 1 feet is equal to 0.3048 meters, and this is raised to the power of 0.25. Okay, so that way, so what we get is 0.5 into 1 by 1.8 power 1.25 into 1 by 0.3048 raised to 0.25 into delta T power 1.25 in degree Celsius, different distance in meters per 0.25. Okay. Upon simplification, what we get is 0.323 delta T power 1.25 by D power 0.25. Okay, so to equate, what we have to do? In the left hand side, we are multiplying by a factor of 7.5 into 10 power minus 4 to get it in kilocalories per meter square per second. So what we have to do is, we have to multiply 0.323 into 7.5 into 10 power minus 4 delta T power 1.25 divided by D power 0.25. So this will become 2.4 into 10 power minus 4 delta T power 1.25 by D power 0.25. Therefore Q by A is equal to, so the Q by A is in kilocalories per meter square second. So that is the required answer. The unit of this kilocalories per meter square second. So if I want this kilocalories per meter square hour, then I multiply this term by 3600 second equal to 1 hour. Okay. So 2.4 into 10 power minus 4 multiplied by 3600. So what we get? 0.864 divided by D power 0.25. So this is our value in kilocalories per meter square hour. So 0.864 is the value when I express this Q by A, that is heat flux, heat loss per unit area in kilocalories per meter square hour. The value will be 0.864. So if I am expressing the same in terms of kilocalories per meter square second, the value is 2.4 into 10 power minus 4. Okay. One correction I want to make, I think somewhere I told D is distance, it is diameter of the pipe. Okay, so that correction we should note. Delta T is temperature difference, D is diameter. So whatever expression we have, delta T by D, delta T is temperature difference, D is diameter. The next problem is, convert, that is heat flux from the surface of a pipe is given as Q equal to 7.38 into delta T power 1.25 D power 0.25, where Q is in watts per meter square, temperature is in Kelvin, diameter to be in kilocalories per feet square second, temperature has to be in Rankine, diameter has to be in feet. So what are the conversion factors? You know that 1 watt is equal to 1 joule per second, 1 calorie is equal to 4.186 joule, 1 feet is equal to 0.3048 meters. So these conversions, also we know that 1.8 delta degree Rankine is equal to 1 delta Kelvin. So this conversion factor we are not going to notice in this problem. So now what is given in the left hand side? Q is given in Q square A is given in terms of watts per meter square. So what is the conversion factor? 1 watt is equal to 1 joule per second. And we know that 1 calorie is equal to 4.186 joule. And we have to convert this kilocalorie into calorie to kilocalories. That is 1000 calories is equal to 1 kilocalorie into. So we have to convert this meter square to feet. So we know that 1 feet is equal to 0.3048 meters, and this needs to be squared. So then what you have is watts getting cancelled, joule getting cancelled, calorie getting cancelled, meter square getting cancelled. So what you have is kilocalorie per feet square on this second. Okay, so what do you get? So 0.3048 square divided by 4.186 divided by 1000. Calculate and tell me what is the value. Yes, 2.22 into 10 power minus 5. So similarly, right hand side we have to multiply by this value to get Q by A in kilocalories per feet square second. So if we take the right hand side, it is given that 7.38 into delta T is given in Kelvin. So what is the factor? 1 delta K is equal to 1.8 delta Rankine. So this needs to be raised to the power of 1.25. Similarly, in the denominator it is given D is in mm. I am doing step by step, but if you know directly you can substitute. You know that 1000 mm equal to 1 meters and 1 feet is equal to 0.3048 meters. So you get meter getting cancelled, mm getting cancelled. So this much is raised to the power of 0.25. So what we get is 7.38 multiplied by 1.8 power 1.25 into delta T power 1.25. So this will be in Rankine divided by, this is 1 by 304.8. The inverse of 304.8 is 0.0033, which needs to be raised to the power of 0.25 and D power 0.25. Okay, so what we get is 64.2 delta T power 1.25 divided by D power 0.25. Okay, so now, so in the left hand side we have found a conversion factor. Q by A is 2.22 into 10 power minus 5 kilocalories per feet square second. So we have to do the same here. Therefore Q by A is equal to 64.2 multiplied by 2.22 into 10 power minus 5 delta T power 1.25 by D power 0.25, which is equal to 1.425 into 10 power minus 3 delta T power 1.25 by T power 0.25. So which is a required expression where delta T will be in Rankine and D will be in feet. in fluid mechanics, we will be determining the volumetric flow rate. That is, what is the rate at which the fluid is flowing across a pipeline can be determined using some flow measuring devices. Some of the flow measuring devices are venturi meter and orifice meter. The orifice meter is essentially a plate with a hole at the center. Okay, so applying Bernoulli's theorem. So Bernoulli's theorem says total energy is constant at a point. So at 2 points, if you compare, that energy at one point should be equal to total energy at another point. So orifice plate refers to a sheet with a hole at the. Okay, the conductance of a fluid flow system is defined as volumetric flow rate referred to a pressure of 1 torr, that is 133.3 kilopascal for an orifice. Conductance can be computed from C is equal to 89.2 into area multiplied by square root of temperature and molecular weight. So the C has a unit of feet cube per second, where A is area of the orifice in feet square, T is temperature of the fluid in degree Rankins, M is the molecular weight of the fluid, it can be kg per kilomole. Convert this equation into SI units. What are the conversion factor we'll be using? You know that 1 feet equal to 0.3048 meters, 1 Kelvin equal to 1 degree Rankins. So because only length unit is there, temperature unit are there, we should be able to easily convert this one. So what we have to do, left hand side is C, which is in feet cube per second, so that we have to convert to meter cube per second. Similarly, in the right hand side there are two things we have to substitute, area and temperature. Area is in feet square, we have to convert to meter square. Temperature is in Rankine, we have to convert to Kelvin. Molecular weight will remain the same, so we need not touch that term M. Okay, we should be able to solve it now. Come on. So first let us take the left hand side, where C is given in feet cube per second. What is the conversion factor? 1 feet is equal to 0.3048 meters, so power 2 cube, so what we get is 0.028 meter cube per second. Okay, similarly what happens to the right hand side? So this left hand side has to be multiplied by 0.028 to get the units in meter cube per second. Okay, similarly in the right hand side it is given 89.2 area is given in feet square. Okay, how to convert this feet square? Again, 1 feet is 0.3048 meters, which needs to be square multiplied by temperature is there, square root of T, right? So if I say square root of T, which is in degree Rankine, conversion factor is 1.8 degree Rankine to 89.2 into 0.3048 square divided by 1.8 power 0.5 into square root of t. See, here this feet square will get cancelled, Rankine gets cancelled to get Kelvin. So what is the final value we get? Is equal to 6.18 square root of t by m. So therefore C is equal to 6.18. C is there. Area is there. Okay. Only we are converting the unit of area. 6.18 ATM into 0.028 will give me the final answer we will get. Okay, that is 6.18 into 0.028 multiplied by a square root of t by m will give me C in meter cube per second. So C in meter cube per second is this right hand side value multiplied by the conversion factor for feet cube per second if we do. So we get, finally what we get is 0.173 a square root of t by m. So where a is in meter square, so that's what we have done here. It will become, a will become, feet square get cancelled, we get meter square. Temperature will become Kelvin. So a is in meter square, t is in Kelvin, and your C is in meter cube per second. So the answer is C is equal to, right here, C is equal to 0.173 a into square root of t by m is the equation where C is meter cube per second, a is meter square, and t is in Kelvin. So this is the required answer. Another problem in unit conversions of empirical equations is the effective heat capacity of a mixture of gases is given by CP is equal to 7.1 T plus 0.577 into 10 power minus 3 temperature T plus 0.0248 into 10 power minus 6 T square, where CP is in BTU pound mole degree Fahrenheit and T is in Fahrenheit. T is in degree Fahrenheit. First part is, what are the units of the constant in the equation? That is, there are three constants. First term, second term, and third term. So this is, there are three terms, 1, 2, 3. So there are three constants in each term. First term, second term, and third term. So if you are looking at it, the left hand side it is given BTU per pound mole degree Fahrenheit. So the unit of the first term is 7.13 BTU per pound mole degree Fahrenheit. So let us solve this conversion of empirical equations from one unit to another unit system. The effective heat capacity of a mixture of gases, the effective heat capacity of a mixture of gases is given by Cp equal to 7.13 plus 0.577 into 10 power minus 3 t plus 0.0248 into 10 power minus 6 t square, where Cp is in British thermal units per pound mole degree Fahrenheit and temperature is in degree Fahrenheit. So we will do two parts now. First part is what are the units of the constant in the equation. B part is change the equation into the form in which Cp is given in kilojoule per kilomole Kelvin and temperature is in Kelvin. I am repeating. The effective heat capacity of a mixture of gases is given by Cp equal to 7.13 plus 0.577 into 10 power minus 3 T plus 0.0248 into 10 power minus 6 T square, where Cp is in British thermal units per pound mole degree Fahrenheit and temperature is in degree Fahrenheit. First part is what are the units of the constant in the equation. Second part is change the equation into the form in which Cp is given by kilojoule per kilomole Kelvin and the temperature is in Kelvin. We should know that whatever is the unit in the left hand side is equal to the units of each term in the right hand side. That means if the left hand side unit is BTU per pound mole degree Fahrenheit, so the unit for the first term is going to be 7.13 BTU per pound mole degree Fahrenheit. The second term including T, that is 5.77 into 10 power minus 4, T will have the unit of BTU per pound mole degree Fahrenheit. Third term 2.48 into 10 power minus 8, T square will have the unit of BTU per pound mole degree Fahrenheit. So this is a unit of the total term, that is here only constant. Here including T, the unit will be equal to the left hand side. Here including T square, the unit will be equal to the left hand side. Okay, so that's why we have written BTU per pound mole degree Fahrenheit for all the terms. Now including T unit is with degree Fahrenheit, means without T what should be the unit of this constant? So that is the question. So T is there, means T is given in the question, it is given in terms of Fahrenheit. T is given in the terms of degree Fahrenheit. So that way, so this T unit will get, after getting cancelled, what will be the unit? Because when we multiply by T, the unit of this total term is BTU per pound mole degree Fahrenheit. That means 1 degree Fahrenheit gets cancelled, then we are getting final unit. That means the original term, the unit of the constant is BTU per pound mole degree Fahrenheit square. So that's why when I multiply by this T degree Fahrenheit get cancelled and finally we end up with this unit. Similarly, in this term BTU per pound mole degree Fahrenheit cube. So then only when we multiply by T square, that is T degree Fahrenheit square, this Fahrenheit square gets cancelled and we wind up with this unit. So that will be the unit of this term. So what we can write is, so the unit of 7.13 is BTU per pound mole degree Fahrenheit. So the unit of second term constant, that is 5.77 into 10 power minus 4 BTU per pound mole degree Fahrenheit square. The unit of the constant 2.48 into 10 power minus 8 is BTU per pound mole degree Fahrenheit cube. So these are the units of the constant in the given expression. That is the answer for part A. Okay, so I am repeating. So the first term in the given expression is 7.13, which has no T in the term. So that way, whatever is the unit of the CP, 7.13 will have the unit of CP. Okay, so in the second term, we have T coming into the picture. So that means when a unit of T, when multiplied by degree Fahrenheit, should get the unit of CP. So that way 1 degree Fahrenheit has to get cancelled. That's why we can write it as BTU per pound mole degree Fahrenheit square. So then it gets cancelled to get this one. Similarly, here T square is there. So degree Fahrenheit square should get cancelled to get the final unit of the term. So that way it should be BTU per pound mole degree Fahrenheit cube. Okay, that is, this is degree Fahrenheit in the denominator, here degree Fahrenheit square and degree Fahrenheit cube in the denominators. So those are the units for the given term which we have written here. So that is the answer for part 1. Now if you look at this expression, second part is change the equation into the form in which Cp is given in kilojoules per kilomole Kelvin. So we have to convert this unit to this unit system. Okay, and temperature should be reported in Kelvin, whereas it is given in degree Fahrenheit here. So we have to convert degree Fahrenheit to degree Kelvin, and we have to convert the British thermal units to kilojoules, kilomole Kelvin. So that's what we are supposed to do here. So it is given that 1 BTU per pound mole degree Fahrenheit. Right? So first time is to convert this 1 BTU. What is the conversion factor? 1055 joules. Okay, so we want to express it in kilojoules. That is 1000 joule is equal to 1 kilojoule into 1 pound mole is equal to 0.4536 kilomole. I am repeating, 1 BTU per pound mole degree Fahrenheit. So to conversion factor, 1 BTU is equal to 1055 joules. 1000 joule is 1 kilojoule. 1 pound mole is 0.4536 kilomole. So if we simplify, BTU gets cancelled, joule gets cancelled, and this pound mole gets cancelled, and we have to simplify this. 1.8 degree Fahrenheit is equal to 1 delta degree Fahrenheit. So this is delta actually. 1.8 Fahrenheit is equal to 1 Kelvin. So Fahrenheit gets cancelled. So what we get is 4.186 kilojoule per kilomole Kelvin. So the left hand side we have to multiply by 4.186 to get in required units of kilojoule per kilomole Kelvin. Similarly, the right hand side term also needs to be multiplied by 4.186 to get in kilojoules per kilomole Kelvin. So before that, this right hand side, the right hand side term as a function of temperature in degree Fahrenheit needs to be converted to temperature in Kelvin. Whatever is the factor in the left hand side we are multiplying, same should be done in the right hand side. The right hand side conversion factor, we have to get temperature in Fahrenheit to temperature in Kelvin. So what is the conversion factor? Temperature in degree Fahrenheit is equal to temperature in Kelvin minus 273.15 into 1.8 plus 32. So this is the conversion factor. So now we have to replace this into this. So how to get this one? It is 1.8 Tk, 1.8 into Tk, 1.8 into 273.15 will get in minus, and plus 32 will give us minus 459.67. So in this expression, that is in the given expression, we have to replace it with this one. Okay, so how to do that? Okay, in the question it is given that 7.13 plus 5.77 into 10 power minus 4t plus 2.48 into 10 power minus 8 to t square. So that we should first write down. 7.13 plus 5.77 into 10 power minus 4t plus 2.48 into 10 power minus 8 t square. Okay. So this T is in degree Fahrenheit, and to replace this temperature in Fahrenheit to temperature in Kelvin, we have to replace with this term. So this is equal to 7.13 plus 5.77 into 10 power minus 4 into 1.8 T minus 459.67 plus 2.48 into 10 power minus 8 into this is t square, right? So that's right, 1.8 tk minus 459.67 whole square. Okay, now we have to simplify this. So what we have done is, first we derived the we simplified the conversion factor from Fahrenheit to Kelvin as temperature Fahrenheit equal to 1.8 temperature in Kelvin minus 459.67. Okay, that is standard conversion between Kelvin to Fahrenheit. So now we have given right hand side of the expression. This is the right hand side expression given, and in place of T we have replaced 1.8 T minus 459.67. Similarly, the suffix is K to mention that this temperature is in Kelvin. 2.48 into 10 power minus 8, 1.8 K minus 459.67 whole square. Now here the expression is A minus B whole square. So A minus B whole square is equal to A square plus B square minus 2AB we have to make use of. That is, this expression needs to be expanded and multiplied by this term, and this needs to be multiplied by with this terms into the bracket. Okay, so to write it, 7.13 plus 5.77 into 1.8 is 1.04 into 10 power minus 3 t minus 459 into this is equal to minus 0.265. Okay, and this needs to be expanded first. So let us just expand. 2.48 into 10 power minus 8. What is A square? 1.8 whole square. That is 1.8 T square plus 459.67 whole square minus 2 into 459.67 into 1.8 t. Now we have to expand these terms. So these first three terms are going to be the same. Okay, so that is 7.13 plus 1.04 into 10 power minus 3t minus 0.265 remaining the same, and then this is 1.8 whole square into 2.48 into 10 power minus 8. So how much we get is 8. This is plus term 8.04 into 10 power minus 8 t square, and this is going to be this multiplied by this, we got to get is minus 4.1 into 10 power minus 5 t, and this plus term is 459 square into 2.48 into 2.48 into 10 power minus 8 is 0.00524. We are expanding this. So first three terms are same. So here what we are doing is 1.8 square t square, that is 8 into 10 power, this is 1.8 square into 2.48 into 10 power minus 8 into t square. That's the first term. Second term is this 2 into 459.67 into 2.48 into 10 power minus 8 is 4.1 into 10 power minus 5 t, and then this constant term, that is 459.67 square into 2.48 into 10 power minus 5 is 0.00524. So now we have to simplify these total terms. So constant terms are there, three constant terms, 7.13 minus 0.125 and then these three. So summing all these three terms, what we get is 6.87 plus there are two t terms. Here one t term is there, here one t term is there. So when you combine these two, what we get is 9.99 into 10 power minus 4 t, and there are only one, there is only one t square term, that is 8.04 into 10 power minus 8 t square. Okay, so this is the right hand side term what we get. Okay, as I said, from the left hand side term we are multiplying by 4.186 is equal to right hand side term also what we are getting, we have to multiply by 4.186 to get the required units. So that is what is when you multiply this one, what you are doing, Cp in terms of temperature unit in Kelvin, what we get is Cp in Fahrenheit multiply by 4.186. So when I multiply by 4.186 into this right hand side value 6.87 plus 9.99 into 10 power minus 4 t plus 8.04 into 10 power minus 8 t square. So once we multiply we get the final answer. So Cp in Kelvin is, what is this, what is the value, 4.186 into 6.87 is 28.16 plus 4.18 into 10 power minus 4 t square plus 3.366 into 10 power minus 7 t square. So that is the answer. solving, what we have done, so we are getting the conversion factor for Fahrenheit to Kelvin as Tk, temperature in Fahrenheit is equal to 1.8 into Tk minus 459.67. Okay, so the right hand side of the given expression is as it is given. We have written. I just converted to one digit, means decimal point coming after one digit, so that when I use the calculator it will be easier for me. Okay, so what I have done is, in place of t we have substituted this 1.8 t minus 459, and in place of t square we have substituted this 1.8 t minus 459 whole square. Then we have simplified, and once we simplify, what we get is 6.87 plus what we get is 6.87 plus 9.99 into 10 power minus 4t plus 8.04 into 10 power minus 8t square. So once we have done that, so this is the right hand side of the given expression in terms of this, and in the given expression left hand side we have to multiply it by 4.186 to get Cp in terms of kilojoule per kilomole Kelvin units. So that way we have to multiply by the same factor in the right hand side. So that's why 4.186 when multiplied by this, whatever we got for RHS, so we get final answer as 28.16 plus 4.18 into 10 power minus 4t square plus 3.366 into 10 power minus 7 t square. So that is the answer. So this Cp is having the unit of kilojoule per kilomole Kelvin, and right hand side this temperature is in Kelvin and this temperature is also in Kelvin. So that is the conversion of an empirical equation from given units to the required units. Thank you. So till now we have seen few examples for converting empirical equations from one unit to another required unit. Okay. So remember, whatever is the unit mentioned in an empirical equation, the substitution of values should be in the specified units only, otherwise we will get incorrect answers. Okay, I will give you some more examples, we can try to solve it.